As a part of Boston analysis, in our lecture series, today we are going to see a derivation on dynamics of synchronous machine rotor, where we will be using various notations, and now we are going to introduce it. So, where E, Ke represents magnetic energy, and J represents moment of inertia in kilogram per meter square, whereas omega Sm represents the synchronous speed in mechanical radians, and omega S represents synchronous speed in electrical radians, and small p represents number of poles, capital M represents moment of inertia with respect to electrical radians, and S represents the power rating, H represents inertia constant, F represents frequency, and del M represents angular displacement of the rotor for stationary reference with respect to mechanical radians, and del represents angular displacement with respect to electrical radians, and theta M and theta represents the angular displacement of stationary axis with respect to mechanical and electrical radians, and T represents time in seconds. Capital T with M represents mechanical torque, TE represents electrical torque, TA represents accelerating torque, and PM represents mechanical power, and PE represents electrical power. So we all know that the equation for kinetic energy is half mv square, where we represent m as the mass and v as velocity. So the same equation is redefined and written as, so instead of kinetic energy we have represented as EKE, which is equal to half into, here we have considered as moment of inertia and synchronous speed instead of velocity. Instead of mass we are considered as moment of inertia. So we know that omega Sm is equal to 4 pi f by p. From here omega S can be written as 2 pi f. So this equation becomes omega S is equal to p by 2 into omega Sm, or we can rewrite as omega Sm is equal to 2 omega S divided by p. And now this is equation number 2. So by substituting equation 2 in 1, we get Ek is equal to half J. Instead of omega Sm, we have substituted 2 by p into omega S. So 2 by p whole square into omega S into 10 power minus 6, where we are representing it in megajoules. So this equation can be redefined as Ek is equal to half m into omega S, where m is considered as J 2 by p whole square into omega S. So this term we have considered it as m. So the equation becomes half m into omega S. Mark it as equation number 4. So to calculate inertia constant, so the definition for inertia constant is the ratio of stored kinetic energy divided by machine rating. So stored kinetic energy, which is we have represented as Ke divided by power rating is Cs. So instead of Ke, from equation 4, we can substitute 1 by 2 m into omega S whole divided by S. So which is one equation for inertia constant, which can also be written as H is equal to 1 by 2 into J omega Sm square divided by S. So let us mark this as equation number 5 and let us mark this as equation number 6. So from equation 5, so moment of inertia m can be written as 2hs divided by omega s, where we can substitute omega s is equal to 2 pi f. So m equation becomes 2hs divided by 2 pi f. If we cancel 2, we will get an equation of hs divided by pi f. So the unit for this will be in terms of electrical radians. So to convert the electrical radians into mechanical radians, so the same equation can be substituted with 180 degrees into F. So here we can represent it as mechanical radians. Now to calculate m per units, we already know which is actual by base. So the actual value is hs divided by phi f and base value is, let us consider it is sb. So if we consider s is equal to sb, the same equation m per units becomes h divided by phi f. H divided by pi f in terms of m per units can be written as h divided by 180 f in terms of electrical degrees. So this is the equation for moment of inertia, and in this derivation we have derived the equation for inertia constant. Thank you.